So in the last lecture, we have seen how to use the Milne-Thompson method for finding the analytic function when the real part is given or the imaginary part is given. Okay. Now we will see what happens if the algebraic sum, that is u plus v or u minus v, is given when u is a real part and v is the imaginary part of an analytic function. Then we'll find how to get the analytic function when we are having u plus v or u minus v. So let us see some examples based on this. Okay. So if u plus v or u minus v is given. So let's have an example. So obtain the analytic function f of z is equal to u plus iv such that u plus v is equal to 2 sine 2x upon e raised to y plus e raised to minus y minus 2 cos of x. Okay, so that's what the function is given, and we have to find the analytic function, okay, with this given u plus v. Okay, so we'll go with the solution. Okay, so what we'll be having, we have to find the analytic function. So first step is always f of z is equal to u plus iv. This is what we want to find. Okay, b and analytic function. Okay, so this will be an analytic function, and now we know if we are given with u plus v or u minus v, then we have to go with the pre-processing. So what is the pre-processing we have? So we can multiply. So multiplying equation 1 by I, we have, so what we'll be having, I f of z is equal to I into u plus ib. Okay, so that's what we have. Now this is equal to iu plus I square b. What we know is, since I square is equal to minus 1, so I have iu minus b, or we can write this as I into f of z is equal to minus v plus iu. This is equation 2. Okay, so we write with the usual notation that the real part first and the imaginary part later. Then what we can do is we can add equation 1 and 2. So we can have adding equations 1 and 2, we get. So what we are able to get here, see, you will be having f of z plus I f of z is equal to u plus ib plus minus v plus iu. Okay, so that's what you will be having here. And now this I can write as, this is 1 plus I f of z is equal to u minus v plus I u plus v. Okay, so what I can write is, I can write this as 1 plus I into f of z is equal to capital U plus I capital V is equation 3. Okay, where you can have capital U is equal to u minus v is real part of analytic function 1 plus I into f of z. And what do you have? This v, and capital V is equal to u plus v is imaginary part of analytic function 1 plus I into f of z. See, why I can say that this is analytic function? Because we have considered this f of z is an analytic function. So if f of z is analytic function, that means f of z is differentiable. So f of z is differentiable, then the constant times f of z is also differentiable. And so that's why this is also an analytic function. So this capital U and capital V are the real and imaginary part of this analytic function 1 plus I into f of z. And now we can see what is given to us. So given to us is u plus v. So we have to see whether it is a real part or whether it is an imaginary part. So where you find u plus v, so u plus v is here. So that is going to be capital V. And hence the imaginary part is given. So what we can say here, we have capital V is equal to u plus v is equal to twice sine of 2x. Then this is e raised to y plus e raised to minus y minus 2 cos of 2x. Okay, so this is going to be the imaginary part. Okay, so we can see that this is going to be the imaginary part. So now, if we know that imaginary part is given, so we have to use the Milne-Thompson method for the imaginary part. Okay, so if I want to use for imaginary part, then I have to find out the first order derivatives. Okay, so what I can say is, if we simplify this, capital V is equal to, okay, dividing the numerator and denominator by 2, what I'll have is, I'll have sine of 2x on, what is the term we get here? E raised to y plus e raised to minus y by 2 and minus cos of 2x. Okay, so what we know is, since we know cos hyperbolic x is equal to e raised to x plus e raised to minus x by 2. So this is the formula for cos hyperbolic x. Okay, and hence we have to consider this. Okay, so if I use this one, okay, so what we can have is we'll slightly have the change. This is going to be 2y. Okay, and hence what? Okay, so we'll have this term is equal to 2y and love. So this term is going to be e raised to 2y minus plus e raised to minus 2y by 2. Okay, so using this formula, what we can say is this is hyperbolic cos of 2y. So we can say capital V is equal to sine of 2x upon, you got here, this is cos hyperbolic 2y minus you have cos of 2x. Okay, so this is actually your imaginary part V. So what we know is, if we consider the Milne-Thompson method, then we need to declare the analytic function. So here we have declared the analytic function, and then we know what is the given part. So imaginary part is given. So now what we have to do is we have to follow the second step. So in second step we find the first order derivative of this. So what we can have is, consider it is the imaginary part. So you'll be having psi 1 is equal to dabba v by dabba y. So please be careful. This v is a capital V, and now we have to find out the derivative of this with respect to y. So we can have sine 2x is going to be constant, and then the derivative of 1 upon x. So we'll be having minus 1 upon hyperbolic cos of 2y minus cos of 2x bracket square, and the derivative of this term. So derivative of this term is going to be 2 sine hyperbolic 2y. Okay, so we can say psi 1 of xy is equal to, yeah, it's going to be psi 1 of xy. So we have this is minus 2 sine 2x hyperbolic sine of 2y on cos hyperbolic 2y minus cos of 2x bracket square. Okay, so let this next equation 4. Okay, and now we have to find the derivative with respect to x, and what we have is psi 2 of xy is equal to dabba v by dabba x. So when we are considering the derivative with respect to x, you have to use u upon v rule. So here what we'll have is this v remains as it is, hyperbolic cos of 2y minus cos of 2x into the derivative of numerator. So it is going to be 2 cos of 2x minus, this will be sine of 2x, and the derivative of this. So it will be 2 sine of 2x, because the derivative of hyperbolic cosine 2y is 0. The derivative of cosine is minus sine, so this minus and this minus sign will get plus, and the derivative of cosine is 2 sine 2x. Okay, so here the denominator we have, this is cos hyperbolic 2y minus cos of 2x bracket square. Okay, let us simplify this. So we get here psi 2 of xy is equal to, so simplify this, 2 cos of 2x hyperbolic cos of 2y minus 2 cos square 2x minus 2 sine square 2x, and upon we have cos hyperbolic 2y minus cos of 2x bracket square. Okay, so simplify this, 2 cos of 2x cos hyperbolic 2y minus 2 we can have common, cos square 2x plus sine square 2x upon, what is the term you'll be having, cos hyperbolic 2y minus cos of 2x bracket square. Okay, now we can have this time is going to be 1. Okay, so this is going to be cos square theta plus sine square theta is going to be 1, and so we can write here this is equal to 2 cos of 2x cos hyperbolic 2y minus 2 upon cos hyperbolic 2y minus cos of 2x bracket square. Or I can write psi 2 of xy is equal to 2 cos of 2x into cos hyperbolic 2y minus 1 upon cos hyperbolic 2y minus cos of 2x bracket square. Let it next equation. Okay, so this way we have completed the second step. So we have calculated the first order partial derivative with respect to y and with respect to x. And now what is the third step of Milne-Thompson method? So what we can say is, put x is equal to z and y is equal to 0 in equations 4 and 5 we get. So what we are able to get, see, psi 1 of z0 is equal to, okay, so psi 1 of z0. So in psi 1 we have to put x is equal to z and y is equal to 0. So if I put y is equal to 0, this sign term is going to be 0. So numerator is 0. That's why we get this the term to be 0. So we got this term to be 0, and we have psi 2 of z0. So what is going to be psi 2 of z0? This is going to be 2. Here we have cos of 2z and minus 1. Cos of 0, probably cos of 0 is 1. So here we have, this is 1 minus cos of 2z bracket square. Okay, so what we can write is, we can write this minus 2 in bracket, we can have 1 minus cos of 2z upon 1 minus cos of 2z bracket square. So one bracket will get cancelled here, and hence we have psi 2 of z0 is equal to minus 2 upon 1 minus cos of 2z. But what we know is, we know 1 minus cos of 2 theta is equal to 2 sine square theta. And that's why we can use this formula, and we can write this as, so this is equal to minus 2 upon 2 sine square z. 2 will get cancelled. We can have minus 1 upon sine square z. So if I have minus 1 upon sine square z, I can write this as minus cosec square z. So we get psi 2 of z0 is equal to minus cosec square z. We got the psi 1 is equal to 0. So the third step of the Milne-Thompson method is completed, and hence we can go for the final and main step. Okay. So final step, what we write is, by Milne-Thompson method, the analytic function here, the analytic function is 1 plus I into f of z. Remember that these are the derivative of capital V, and capital V is the imaginary part of 1 plus I into f of z. So you must be careful here. We are applying Milne-Thompson method to this function. Okay, so is given as, what you will be having. So always write the formula. So 1 plus I into f of z is our function, and integration we have psi 1 of z0 dz plus I integration psi 2 of z0 dz plus the constant of integration. So constant of integration I am choosing here C1 purposely. So later you will understand the purpose of choosing C1 here. So I'll write where C1 is constant of integration. Okay, so C1 is going to be constant of integration. And now write down the values. So we have 1 plus I into f of z is equal to, this is going to be 0 dz plus I. This is minus cosec square z dz and plus c1. So it is I, and you have integration minus cosec square z dz plus c1. So what we know is, since d by dx of cot x is equal to minus cosec square x, and so the integration of minus cosec square will be cot x, and hence this is what you'll be having, I into cot of z plus c. Okay, so what we got here, we got, this is 1 plus I into f of z is equal to I cot z plus c1. Okay, so we got the analytic function which was expected in equation 3, but we are interested in equation 1. So we are interested in only f of z. So what we can do is dividing of equation by 1 plus I, we have. So what we'll have is f of z is equal to I upon 1 plus I into cot z plus c1 upon 1 plus I. So as we know, c1 is a constant, constant upon constant. This is going to be the another constant. And so instead of this, what we can do is we can write only one constant. So we can write here, hence f of z is equal to. I upon 1 plus I into part of Z plus C. Okay. I write this as only C. Okay. And this is what you'll be having. So is required analytic function. Okay. And what is C is where C is equal to C1 upon 1 plus I is constant. Okay. So here what was given to us. So the given thing was u plus v, and using this u plus v, okay, we have calculated the analytic function. So how we started? First we assume the function, then we multiplied by I, then we added this term. Then after that we identified whether the real part is given or the imaginary part is given. Now in this case the imaginary part is given, and hence as imaginary part is given, we applied the Milne-Thompson method for the imaginary part, and then using the first order derivatives and substituting x is equal to z and y is equal to 0 by using the Milne-Thompson method, we got the function 3 first. So we'll get the function 3 1 plus I into f of z, and later on if we remove this constant on the left hand side, then we are able to get the required analytic function on the right hand side. So this way we have to use the Milne-Thompson method when the sum or difference of the real part and imaginary part of the function are given. Okay. So do you have any doubt in this example? So is there any doubt in this example? Okay, that's good. No problem. So we'll have one more example based on this. Okay, so let's have the example. So find the analytic function f of z is equal to u plus iv, where u plus v is equal to e raised to x cos y plus sin y plus x minus y on x square plus y square. Okay, so this is given. Now you can identify that this is going to be again a imaginary part. Okay, so but we have to write all the steps properly. Okay, so don't be in hurry. Write each and every step properly so that the reader will understand. And hence we write let f of z is equal to 2 plus iv equation 1 p and analytic function. Okay, so this is an analytic function. Then what is the next step? We have multiplying equation 1 by I we get. So what we are able to get is I into f of z is equal to I u plus iv. So it is going to be iu plus I square b. Since I square is equal to -1, so I can write this as I into f of z is equal to minus v plus iu equation 2. Okay, so once we have equation 1 and equation 2, we add this. So what we can do is adding equation 1 and 2 equations. Equations 1 and 2 we have. So what we'll be having 1 plus I into f of z is equal to u plus iv plus minus v plus iu. Okay, and hence we get 1 plus I f of z is equal to 2 minus p plus I u plus v. Okay, now we can write this as hence 1 plus I into f of z is equal to capital V plus I capital B. This equation 3. Okay. Now what we have, so where capital U is equal to U minus V is real part of analytic function 1 plus I into f of z, and V is equal to U plus V is imaginary part of analytic function 1 plus I into f of z. So what we have given, see what you have been given, this is again an imaginary part. So we can write here, we have we'll be having capital B is equal to U plus V, that is e raised to x cos y plus sin y plus x minus y upon x square plus y square. Okay, so that's what we have. And now consider the first order derivatives of this capital B. So we have psi 1 of xy is equal to, so what is going to be double b by double y. Now we have to find out the derivative of this term with respect to y. So be careful. This e raised to x remains as it is, the derivative of this term. Okay, because this does not contain any y, so this term is treated as a constant. So derivative of cos y is minus sin y plus derivative of sin y is cos y plus. So here we have to use u upon v rule. So we'll be having x square plus y square. The derivative of u is minus 1 minus x minus y, and the derivative of v is 2y. Upon we have x square plus y square bracket square. Okay, so we have to simplify this. So we'll have e raised to x minus cos y plus sin y. This time is okay. Here we have to simplify plus minus x square minus y square. This term here you have minus 2xy minus minus plus, we'll be having 2y square upon we have x square plus y square bracket square. Okay. So now simplify this. So we get psi 1 of xy is equal to e raised to x minus cos y plus sin y plus. So this is minus y square,
Sir,
2y plus 2y square. Yeah.
it should be cos y minus sin y.
Yeah. Okay, so you're right. Okay, so it is minus sine y plus cos y, or I can write this as cos y minus sine y. Easy. Okay, so here what is the term I'll be having? So this is y square minus 2xy and minus x square upon x square plus y square bracket square. So let this next equation. Okay, remember that this is not a perfect square because we have minus x square here. If it would have been plus x square, then it would have been a perfect square. So it is not here. Okay, and now we have to consider, the derivative with respect to x. So psi 2 dabba v by dabba x. Now here the derivative of e raised to x is e raised to x itself. So it remains as it is, e raised to x will be having cos y plus sine y. Okay, and now plus again we have to use u upon v rule for this also. Okay, so if I use u upon v rule, now we have to find the derivative with respect to x. Okay, so let us see what you have here. X square plus y square, the derivative with respect to x is 1 minus x minus y, and the derivative will be 2x upon you will be having this is x square plus y square bracket square. Okay, so now simplify this. So I will be having psi 2 of xy is equal to e raised to x cos y plus sin y plus this time we will be having x square plus y square minus 2x square minus minus plus 2xy, and that's what we will be having. Now see here, this term we will have x square plus y square bracket square. Simplify psi 2 of xy is equal to e raised to x cos y plus sin y plus this term is again y square plus 2xy minus x square upon x square plus y square bracket square. So this is equation 5. So we have completed the second step of Milne-Thompson method. Now we have to consider the third step. So what we will have the third step? Then we will put x is equal to z and y is equal to 0 in equations 4 and 5. We have. So what we will get is, see, psi 1 of z0 is equal to. Okay. So psi 1 of z0 is going to be e raised to z. Cos of 0 is going to be 1. And this term is going to be 0. So it will become, this term will become e raised to z. So we put this going to be e raised to z. Now next term. So what we have the next term. See, this term is 0, this term is 0, this is minus z square, and this term is z square plus 0 bracket square, so z raised to 4. So we'll have here, this is going to be minus z square upon z raised to 4. So I can write this as e raised to z minus 1 upon z square. So we got psi 1, okay, is equal to e raised to z minus 1 upon z square. And what will be psi 2 of z0? So this is again e raised to z. This term is minus z square upon z raised to 4. So it is e raised to z minus 1 upon z square, and hence we got psi 2. So we have psi 2 or z0 is equal to, so it is going to be psi 1 of z0. It is e raised to z minus 1 upon z square, e raised to z minus 1 upon z square. So we got psi1 and psi2 at z0. So the third step of Milne-Thompson method is completed, and now we have to go to the fourth step, fourth and final step. So what we'll be having by Milne-Thompson method, the analytic function 1 plus I into f of z is given as. So what we have 1 plus I into f of z is equal to integration psi1 of z0 dz plus I integration psi2 of z0 dz and plus c1. Now you know why I am writing c1. So where c1 is constant of integration. Okay, this c1 is going to change, so that's why I'm writing c1, and at the final step I'll be writing c only. Okay, and now what we get is we have 1 plus I into f of z is equal to integration e raised to z minus 1 upon z square dz plus I integration e raised to z minus 1 upon z square dz and plus c1. So we got here the integration of e raised to z is e raised to z plus 1 upon z plus I. The integration of e raised to z is e raised to z. The integration of this is plus 1 upon z and plus c1. Okay, now we can see this term is same. So we can write this as this is equal to 1 plus I into e raised to z plus 1 upon z plus c1. So this is 1 plus I into f of z. So by Milne-Thompson method we have obtained the analytic function 3, but we are interested in f of z only. So what we have to do is divide this equation by 1 plus I on both sides. So we can say dividing above equation by 1 plus I on both sides we get. So what we'll get is we get f of z is equal to, this will get cancelled. So we'll be having e raised to z plus 1 upon z plus c1 upon 1 plus I. And hence I can write f of z is equal to e raised to z plus 1 by z plus c. Okay, so you can have this is the required analytic function. Okay, we can write here where c is equal to. Okay, so what is c here? c1 upon 1 plus I. Okay, so this way we are able to get the analytic function as the u plus v was given to. Okay. So do you have any doubt in this example? That's great. Okay. So let us see one more example based on this. So we can have the question. Okay. Find the analytic function f of z is equal to 2 plus iv such that 2 minus v equal to x square minus y square minus 2xy. Okay, so that's what we have. So here it is given that u minus v is equal to x square minus y square minus 2xy. So we go with the solution. What we have is that f of z is equal to u plus iv. That is equation 1. B and b and analytic function. Okay, so what is the next step? Multiplying equation 1 by I we have. So what will be having I f of z into I is equal to I u plus iv. This is equal to iu plus I square v. Since we know I square is equal to minus 1, so I can write I into f of z is equal to minus v plus iu, equation 2. Okay, so next step we have adding equations 1 and 2. We get, what we'll get is 1 plus I into f of z. 1 plus I into f of z is equal to u plus v plus I. So here we have 2 minus v plus I u plus v. And hence we can write 1 plus I into f of z is equal to capital U plus iv. Okay, so this is equation 3. Here what we have, so we can write here u is equal to u minus p is real part of analytic function 1 plus I into f of z, and p is equal to u plus v is imaginary part of analytic function 1 plus I into f of z. So please be careful for writing this all. Okay, because the reader will understand what you will write. Okay, so that's why for the understanding of reader, you must write everything properly. And hence, what we have given. So we have been given u is equal to u minus v. So that is x square minus y square minus 2xy. Okay, so this being a real part, we have to use the Milne-Thompson method for the real part. And hence, what we have consider phi 1 of xy. So what is phi 1 of xy? W by wx. So it is 2x minus 2y. Let this equation 4, and phi 2 of xy is w by wy. So it is minus 2y minus 2x. So here this is going to be equation 5. Now we have completed the second step of Milne-Thompson method. So let's go for the third step. So what is the third step? Put x is equal to z and y is equal to 0 in equations 4 and 5. We have, so what will be having? We have I1 of Z0 is equal to, so this is going to be 2Z, and I2 of Z0 is minus 2Z. So this term will be 0, this term will be 0, this is 2z and this is minus 2z. And now the final step of Milne-Thompson method, the fourth and final. So we'll be having by Milne-Thompson method, the analytic function 1 plus I into f of z, okay, is given as. So please be careful while writing the analytic function, because according to this you have to write a formula. So we have 1 plus I into f of z is equal to integral phi 1 of z0 dz minus I integral phi 2 of z0 dz and plus c1. So what we have where c1 is constant of integration. Okay. Now we know this is 2z and this is minus 2z. So we can write this. So we get here as this is 1 plus I into f of z is equal to. So this is going to be 2z dz minus I, and this is minus 2z dz plus c. So I can write this is going to be z 2z square by 2 minus minus plus I 2z square by 2 and plus c1. So we can write z square plus iz square plus c1. So we can have 1 plus I into f of z, and this is equal to, we can have this z square common. So I can write 1 plus I z square plus c1. Okay. Now we are interested, we got 1 plus I into f of z, but we are interested in f of z only. So what we can do is dividing above equation by 1 plus I on both sides we get. So what we are able to get is, we are able to get f of z is equal to z square plus c1 upon 1 plus I. So we can write this as f of z is equal to z square plus c. Okay. So we can write this as, this is the required analytic, okay, where c is equal to c1 upon 1 plus I is, okay. So this way we are able to get the analytic function f of z if we know u plus v or u minus v. So do you have any doubt in this example or in this method, or the examples up to it we have solved? Okay, so we don't have Any doubt? That's good. Okay. Fine. So that's great. You don't have any doubt.